Okay, sidewall friction. In this lecture, we'll talk about sidewall friction, which is the inclusion of the friction between the side of the ramp walls and the soil on either side. You could think of this as the soil on either side. I've drawn a little graphic up here on the right. The soil on either side of the abutment kind of clamping and rubbing on the ramp walls to kind of add capacity or resist sliding. It's a bit more complex than just taking the active force from the soil wedges and multiplying by the coefficient of friction. But instead, we will use equation 3.24 from a thesis that I've attached from 2016, and we can apply this equation to each side of the abutment acting on as one large anchor block, or rather, each side of the abutment acting as one large block in general. And I'll break down this equation by each term. So we have Fs, our frictional resistance, and we want that to be ultimately in kilonewtons. We multiply by 2, which is going to be a multiplier for both sides. Then we have K naught, which, as you may remember from previous lectures, is the coefficient of lateral earth pressure at rest, which is 1 minus sine phi prime. Phi prime is the effective internal angle of friction. So when we talk about effective internal angle of friction or effective anything in terms of geotechnical engineering, this is just we are including the water table effects. So if there is water present, the internal angle of friction can change, the unit weight of the soil can change, so we add that prime to account for it. And this is taken as 30 degrees unless we've changed it otherwise. We have the effective unit weight of the soil in kilograms per cubic meter. We have H average, which is the average embedment below the soil surface. And remember, we're going to ignore the top 30 centimeters. This is just a conservative estimation. We can assume the top 30 centimeters are probably going to get disturbed during construction. It hasn't consolidated, it's not confined, and it's probably not going to be achieving the force that we are assuming it will, so we're going to ignore those top 30 centimeters. B is the height of the embedded wall, so the height of the embedded ramp wall. And delta is the angle of friction or the angle of external friction between the soil and the surface. And this is taken as 0.5 phi prime. Finally, T is going to be our length of embedded wall. So you can see the full equation here, and now drawn some of these variables out for you in a little diagram. We can get our average embedment from the average between the embedment depth in the back and the embedment depth in the front of the abutment, remembering to ignore those 30 centimeters. We can take our T as the distance from the back of the anchor to the front of the foundation. And in our case, H average is equal to B, so H average minus B over 2 is just going to be H average over 2, so you'll see how that equation can simplify. So the equation again, and the diagram again, and we can implement this into our capacity for the abutment sliding.